Super. Okay, so it's 2 a.m. in the morning and your telephone is ringing. Your boss is calling you because actually the system you were working on for the last 2 years is not working properly. Customers start calling, complaining about the system unavailability. It's quite a stress. So you wake up, but by the time you wake up, get the PC ready, it turned out that actually the system is almost completely down, it's not responding. The boss is calling you again. What is happening? And now it's only you that can restore the system back to the operation. You are working under pressure, right? So if you are lucky and the case is very easy, then most probably after 10 minutes you can go sleep and the system is back to operational. If not, it could be that you won't be able to leave a toilet for the next 30 minutes, right? So everything depends on the importance, majority, and priority and the time. After an hour of investigating the logs, you come up to the conclusion that actually that was the bloody metric systems that kills your system completely. Consume all the CPU and memory available, stopped receiving the request from the customer. And that was the reason the system was down. I'm a solution architect working for Motorola Solutions here in Kraków. My name is Kamil Kowalski. I'm trying to see in individual services and technologies opportunity to build some solutions, some products that can make our life easier. Also, part of my responsibility is to anticipate failures that can happen to the system and pretend the system to cope with them. So that actually, when we receive the call during the night, we know what to do, or the best, we never receive that call. In Motorola Solution, we have a luck that we have the customers that want to pay a lot of money for the software that is reliable, fault tolerance, highly available, and thanks to that, we have a time and the budget to play with a lot of different patterns that should provide you and should give you the system that is highly available. And right now we are going to talk a little bit about it, particularly about the Resilience4j library that is widely used. And as any library, and that was told just the lecture before, that actually taking the library to your system is, you hope to solve some kind of problems, but it's always a trade-off. So you solve some kind of problems and you open a new one. Maybe not the problem, maybe simply the challenges. And I would want to show you today what are the consequences of using the Resilience4j, what you need to take a look while making the decision, what opportunities, what other alternatives you would have, and how you can handle them. But first, try to think about what the resiliency is. And I would want to start with some type of classification of the failure, the basic one, based on the source. So the basic one is, of course, the hardware, right? So there is a layer hardware, and a lot of things happen over there. So hard disk can go wrong, can be faulty. There could be a power outage, there could be overheating, even the Ethernet cable can be broken. So some issues will happen on that layer. Then there is a middle layer, runtime environment. Mostly we consider it as an operating system where you have an access to the file system, you have a scheduler that allocates you the CPU, memory, and then processor time. And that is also some kind of software. It is a software. And that software can also brings you some challenges, can be faulty, can create unpredictable behavior. And then you have a software. A runtime environment for the Java would be JVM, the virtual machine itself. In the Kubernetes, it could be the Kubernetes cluster. And then we have our software, where we are put our business logic. And according to the Gartner's research, the top reasons of the failing software on that software, on our application layer, is the business logic. Very often we are missing the requirements, we don't understand exactly what customer wanted, or the business gives us the wrong directions. So business logic itself, integration with the third party, integrating third-party libraries, integrating with third-party services, performance, so you know exactly that making the software running and running it under the heavy load, this is additional effort that you need to put, and it can also create you problems and be challenging. And the maintenance during the upgrade process, during changing of the configuration, also you can see that actually something can go wrong. So as I told you, each and every layer will have a fault and will create some faults. It's not possible to write a flawless component. The more important is that those issues can leak out from the single layer and then sneak into the dependent components. So runtime environment, on top of creating its own faults, also receive the faults from the hardware layer, and the software layer receive all of them and present them to the customer. And the idea here is that we would want to hide as much as we can such issues from customer. So the customer can see our service as a reliable and available, even though beneath there are a lot of elements that are happening, and they will. And the resiliency, in fact, it's the concept that I don't want to go into the Oxford definition, what is the difference between the resiliency, fault tolerance, and so on. But think about it in a very rational way. So resiliency is some kind of concept that allows you to handle the issues that can exist inside a specific layer, but also to handle the issue that comes from the dependent services. It's not that it's worth to fight for every single failure. If you have on the hardware level, for example, you have a disk drive and you create over there the right system that will provide you a better availability, still there is a possibility that the write access or the latency to access that disk could be a little bit longer than expected, than the average, than the P99 percentile. And it's not worth fighting to make the constant response time 100% of the time. It's use the best is to use the existing technology, apply as much reliability as you can on a single layer, and then teach the dependent layer how to cope with them. And this is exactly what the resilience is and what the Resilience4j library provides you. So let's take a look at some of the issues that are happening actually almost all the time and how to handle them with the resiliency. Transient failure. So this is the short-lasting failure, right? The one that is just, I don't know, the network glitch, some database, a little bit longer transaction that consume a little bit more of the memory, some service that is busy for the short duration of time. This is short-lived, and in a moment it should disappear. So then the thing that we can apply is the simple retry, right? So the moment it's like knocking to the door. You're knocking to the door, no one is answering, you are not leaving, right? You just to make sure you repeat the knocking to make sure that there's no one else. So this is the retry mechanism that we apply, short-lived failures. In a naive attempt, even naive configuration, you are just defining how many times you would want to try and what is the duration between the tries. But There are some challenges related to that. One of them, very important one, although the pattern itself is very strong, is very simple, the consequences could be different. Retry storm. So you can actually use all your resources because of that side effect. Imagine that you have, for example, 5 services, A, B, C, and D. And let's imagine that they are calling each other they are nested and calling each other in a synchronous way. So you are creating the connection, you are sending the data, and the last service is not answering properly, has some issue with the database or anything like that, and providing you 500 errors. Then it's a D service. Then the C service is actually trying to retry it. If you, on top of that, add that, for example, the previous service has a timeout and would want to receive the response already, and the response is not there, and it's trying to apply their own retries, then basically you created a new path, you're creating a new connections. On each and every layer, there is additional connection created that needs to be handled and that needs to be consumed by your system. If the response code is propagated to the service B and C, C and B, and each of them are trying to do the retry, you can see that in a moment there are a lot of retries and a lot of additional communication that is visible in your system. If you don't use it properly, you can actually kill the system, because the fact that one of the services is not able to answer basically means that there is could be some performance issue, and if you increase the load that moment, then basically means that you are making the situation even worse, right? Instead of helping it. So good practice is that think about the retries, limit the number of retries, do not put retries everywhere. This is very often decided by the business logic. Conditional retries is very important. Do not retry on 404 while accessing some resources, right? Because another attempt will not help you much. Or if there is a retry exception like authorization exception, then if you are not able to authorize this time, why you believe that the next time you will be able to authorize? So think about when to apply the retry and handle the responses properly. Very important one also is the interval function. So to prevent killing application with a lot of retries, you are applying the backup strategy, which basically means that you will the first retry will come after, for example, 2 seconds, but the second retry comes after 4, and the third one may be 8 seconds, right? Do not give a time for the service if it is not responding. Give this transient failure to disappear. Give a little bit of time to make it happen. Another one is the side effect. So when you do the retry, this basically means that within your system, there would be a duplicate messages with the same request, the same intent. So if you apply the retry for reading the data from the database, nothing is changed, right? The system is giving you the answer, the state of the system is not changing. But if you are, for example, retrying the attempt to place an order, then basically means that you need to make sure that ultimately you will just place one order, although request was duplicated. Preparing the application for that is not always such easy. You can do a lot of that while applying, for example, UUID for the client request and being able to recognize that this is the duplication of the message. But to solve this kind of problem, I can say that the best answer I can give, yeah, it depends. So based on the business logic, be careful while applying the retries on the system, on the request, on the commands that actually can change the system. Make sure that your system, that your upstream service is idempotent and will not create additional side effects. We had once an issue with that. In our product, we are routing the emergency calls towards the agencies. So when you are calling 112, we are redirecting that call to the specific, to the certain call taker. And actually, due to the retry in our system, the call was generated, the outside call was generated twice, and the call taker was presented with the 2 calls instead of 1. Yeah, in the configuration, you can apply what type of results you would want to apply the retry. You can ignore the exception or retry on a specific exception, or even go into the specific exception to find anything special in any string or anything in the exception itself. A lack of responses. So when the client sends the request to the server, it waits a certain amount of time. It won't wait for an hour, right? It would want to receive the answer. But if the answer is not coming, what to do? So the client very often is applying a timeout. So I will not wait any longer. I need to do something else. I need to apply maybe alternative. So it's also known as a timeout. So the client is just waiting for a specific amount of time for the server. But the request that was sent for the first time is already processed by the server. So in the configuration here, you can see that you can exactly define the timeout duration. Also, you can set the running future to true. This is for completable futures. If you are using Java 8, this is needed. Sorry. Because it's very difficult in Java 8 to cancel and to close the completable future that you don't have. This is an asynchronous call, so you don't have the possibility to control it. And the Resilience4j allows you to do it and allows you to kill it, to cancel the request after you time out from the response. And as I told you, one of the challenge here is that the server is still processing the request. So you are the client. You are sending and placing a new order on the upstream server, and you resign, and you're no longer interested in that, and you will not proceed it. But the server is processing it, and it could be that 10 milliseconds later, it will complete it and will try to send a response to you. But there is no client. Client disappeared. So this is exactly how we should handle such situation. It's handle retry to commands in an explicit way. So when your server is trying to send the response and there is no one, you cannot send it, you got the connection exception because the client already disappeared and closed the TCP connection, then basically you should apply some rollback strategy to roll back the transaction or the activities that was triggered because the client resigned from the request. Of course, you can apply the HTTP headers indicating how long the request is valid, and it will also work. But this is something additional that you need to do by yourself. Alternatives that you can apply. Spring Boot gives you also the timeouts out of the box. You can also use the Envoy sidecar. This is very common to use the sidecars next to your application that is doing that kind of transport activities for you. So applying the retries and other transport patterns. Also, you can subscribe to the events on success and error and timeout on the client side, and then being able to handle such situation on the client side. Prolonged failures. So a little bit longer. I need to control the time as well. So a little bit longer failure that can happen potentially could disappear or not, but it's counted in dozens of seconds, minutes, even sometimes hours. Then we are applying a very, very nice pattern, which is called circuit breaker. It works like then when the service knows that circuit breaker is like a physical circuit breaker, right? So if it is closed, then the communication is flowing. If it is open, then actually there is a break. It is not flowing. And we have also some kind of concept in the middle, which is half open. We'll discuss that in a moment. So basically, when we see that one of our dependent service, upstream service, is not able to respond in a proper amount of time, or the latency of our requests is too long, then there is no point to stress it even more, because it could be that it is fighting for the resources and completing existing transaction. So do not force it to do it. Give it a time and try after some specific point of time. Circuit breaker does it in a very clever way, because it's not a static configuration that please apply after 5 minutes, 10 minutes, and so on, and then give up. Circuit breaker is doing it in a way that it stopped sending the request to service A. Then after, for example, 30 seconds, it will try 2 or 3 requests to see if the service is back to the is back to normal, is giving the proper responses. If yes, then start sending more requests. If no, give it a time again to recover. That concept also can be used and is widely used in the Kubernetes when the service A is talking with a couple of instances of service B. I will give you explain you this concept, how it works in the Kubernetes on the later slides. Great. So what are the challenges related to the circuit breaker? Quite a complex configuration. It's not that you cannot do it. It's not rocket science, but basically a little bit more complex that you do for the regular operation. Basically, as you can see, there are a lot of configuration that you can apply. So what is the threshold? What does it mean that there is a failure, right? That the service is not responding? What is the slow call rate? So if you have, if you would want to do the pushback because of the increased transaction duration, then you need to decide actually how long does it take, and you decide here how long do you mean it's that the request is slow and the transaction is slow. You can also apply this strategy to the time-based window and also to the count-based window. So depending on number of requests or the time when the requests are sent. Also, you apply some exception, what's exception to record, where to go directly into the exception, what exception to ignore. So then when you would want to configure that properly and make sure that the circuit breaker will work as expected, you need to be very careful. It's very good to have a very comprehensive monitoring system and measure carefully what is happening and how your system reacts to that, and if you don't create false positives. You can also use adaptive thresholds. So, for example, those failure rates or the how long the transaction can happen, how long it is acceptable or not, because depending on the system, how your system behaving, is it under the performance tests, under heavy load or not, that value could different. So you can also play with those numbers and apply adaptive threshold by yourself. And provide the fallback. If the service one is not available, you can provide some fallback mechanism, take it from the cache, generate some other response that will be acceptable for the system. Also hardware testing. So as I indicated before, to test that the configuration of that circuit breaker is proper, you will have to play with the dependent services, forcing them to create an errors, to create the delays, and then you can play and see if it works fine. It's very good and very beneficial for the system pattern that you can apply. Also available in the Envoy sidecar, where you delegate that kind of functionality out of your functionality to the external sidecar. Killing dependency. Once we receive a call from the dependent product, hey, what are you doing? What are you doing, guys? Our system is completely killed, and we can see that you flooded us with the messages. And that was true, because actually we didn't apply the rate limiter, and during running our performance test, the number of events we generate was so high that the dependent service received a lot of requests and were not able to control them, to process them. So you can use this. It's also, you can define here what is the period of refreshing the data, what is the duration of the window, so how you count the rate in what type of window, and time duration and limit for the period, and how many requests per that period can be applied. The challenge that we can see here is that when you have the distributed system and you have a lot of clients, independent clients, sending the request to the one upstream server, and you agree with them that you will send no more than, 100 requests per second, then actually if you have 5 clients, in theory, only 20 should be allowed for each of them. If you have 80 or 8 clients, then only 15, and so on, or even less, so 12. And basically, it should be a dynamic value. So in a distributed system, to not exceed the limit, you should use, for example, a distributed cache. So connect the any type of cache, Zookeeper or Redis or anything like that, to share the data, what is the current value, and whether we exceed the limit or not. Also, you can adapt the static configuration with the number of instances. So if you know that for sure you will not exceed more than 5 instances and you have them already deployed in the system, then you can statically put, okay, so just 20 requests per second for each of them, and then you can have it in a static way. And static rate limiting. Server, this is very, very nice. Server still can reject incoming requests. This is because, imagine that the client has a window, let's say 1 second window, and is allowed to send only 2 requests within that window. So the client is sending in one window, just at the end, is sending 2 requests. And then, couple of milliseconds later, the new window appears to the client, and it's sending, at the beginning, this time, another 2 requests. But the window for the server could be a little bit different, and the server will see 4 requests within the agreed amount of time, within the seconds. So it still could reject those 2 requests. So you need to be careful about it. The good practice is that simply make the period for the client a little bit shorter. So for example, 1 every half a second. Then you distribute this in time, and the server can accept them. Use adaptive control, explicit or implicit error. You can also adapt this rate based on the responses you receive from the client. So if you start receiving lots of 4 to 9, too many requests, or that the server is busy, or some exception, then you can even lower the number because there is no point to make it if you get the explicit response that there are too many of them. Alternative rate limiter protection. API gateways, all the API gateways has that rate limiter applied. Internal DDoS. So this is the case that wake us in the middle of the night. It's basically when one lower priority task consume all your resources. And it can happen if the number of this lower priority task is big enough to make your system busy so that you are not able to process the proper request from the system, higher priority. And the bulk heading is the pattern that can help you, because in the bulk head you can decide exactly how many threads you can allocate for the specific bulk head and only allow the specific endpoint to use agreed amount of resources from your service. You are deciding what should be the initial one, what should be the max, and if there are any new requests, they are waiting in the queue, how long the queue should be. But you can split the resources of your service into such a way that failure in one will not affect any of the other resources. This is thread pool bulkhead. It's not very widely used nowadays. I really don't know, probably because this works really well when you have a specific number of threads. So you have the thread pools when you decide, okay, how many for this and for that. Right now, it's a little bit different. There is asynchronous pool of the threads that the asynchronous operation are running. You have virtual threads right now in Java. So this kind of operation is changing the concept of bulk heading. So probably that's why it's not widely used nowadays. The challenges here is that you can throttle the application on your system, even if the system is idle. So if part of the resources are available for the specific operation and the requests are coming, you won't be able to consume more resources, even though other bulk heading bulk-headed resources are available and could be used. You cannot do that. And of course, apply the comprehensive monitoring system so you are sure that the amount of resources you applied is proper and enough. Excuse me. Other resiliency patterns that some of them are not available in the system, in the Resilience4j, but actually I found it very useful. We found it very useful. Of course, cache is even part of the Resilience4j, but load leveling. Load leveling is a very good pattern. So with the load leveling, you have a message broker that can receive the messages from, for example, outside world, and there could be a massive flood of the messages. But on the other hand, on the other side of the system, you have a consumers, specific number of consumers, and those consumers are consuming the messages from the queue with the competing customer pattern, which is they are pulling the data when they are available. They are pulling the data, the messages from the broker, and then process them. So actually, you are splitting the high traffic on the input with, for example, lower pace of consumers. If you would want to increase the pace of consuming the messages, you can just create a bigger number of consumers. So based on the queue depth, you can scale the consumers and create more instances. So this way you will consume messages earlier, but it's the consumer deciding when to take the message, how fast to process it, and you will never kill the consumer this way. Degraded services is alternative. So if you don't have a full capability of creating a proper response, you can apply some from the cache, you can apply them some default values or anything like that. We are also playing with the progressive delivery and progressive deployment. So red-black deployment or blue-green deployment, you also know it as a blue-green deployment, as well as the canary. We are applying our canary strategy to introduce the changes to the system in a very seamless manner. Basically, the canary strategy is that next to the old one, next to the old version of your service, you are deploying a new version of your service and then trigger the downstream client to send to the new version only small portion of customer traffic. So if something goes wrong with the new version, you are just risking, for example, 5% of the whole traffic. And once you realize that, you can do the rollback and stick to the old one, which is working properly. So this way you introduce the change to the system in such a way that, in a gradual way, and you can control on each and every step that everything is fine, and you are not risking the customer traffic. Chaos testing, we also apply the chaos testing. So to make sure that your system, you applied a lot of patterns, right? Retries, circuit breakers, bulk heading or whatever, and even more. And suddenly you just want to make sure that all of them are working fine. So the best would be to apply on purpose the chaos inside your system. Create failures explicitly to trigger those mechanisms and to see that they are working, because they will happen, no more, no doubt, right? You cannot create something, you cannot create a system that will never generate any fault. But if you are prepared for that, then try to test it. Put a chaos and try to test it. Disaster recovery, similar. Imagine that your system completely disappeared. All the VMs that you were deployed on in the cloud provider are gone because there is a massive outage in one of the cloud provider. But your customer will not care about it. It will call you, hey, the system is not working, right? It doesn't matter, it's your fault, it's your cloud provider, it is not working. So you have this mean time to recover, right? When the failure comes, you need to provide the service as soon as possible. And the disaster recovery is how fast you can recover from the complete disaster of your system. Think about it this way. And client-side smart load balancing. This is the best concept. Through all the years, I worked on the highly available and resilient systems because it's not only on the software level, we are applying that on the runtime level and hardware level as well. From all those years, if there is one thing that I would suggest for you, it's exactly client-side smart load balancing, especially in the Kubernetes. Because in the Kubernetes, let's say the retry. In the Kubernetes, we have a client, and the client is generating the request to the upstream services. And let's see that in the Kubernetes, you have 3 replicas, right, of this 3 microservices, 3 replicas of that service. But they are hidden behind the Kubernetes service. Your client is talking with the Kubernetes service, and the Kubernetes service is doing some round-robin load balancing across them. So when the client sends the request, and that request ends in the faulty replica that will give you the response, the client will generate a new attempt, but it will be treated by the Kubernetes as a completely new request. So actually the new request comes, and again, load balance Kubernetes service is trying to find out which one should receive the request. It could be the same that has just answered you in the wrong way. So it will take some time for the Kubernetes to realize that some instance is not healthy. And during that time, with 1, 2, 3, so 1/3 multiple 1/3 1, basically 1 out of 9 requests will end up, both retries will end up in the same faulty system. In a smart client, you have this logic of load balancing on the client side. So the client knows exactly that there are 3 replicas, and the client knows that one of the replica is responding with 500 third time in a row, and immediately will apply the circuit breaking strategy. Or we'll see that one of the replicas latency is doubled comparing to the previous one, so actually will prefer the low latency replica to send the request to. So this is for the retry. I told you already for the circuit breaker, exactly the same. You need to know exactly which instance you are not going to send the request to. So applying just the Resilience4j in the Kubernetes, where you are using the Kubernetes services, will not help you much. Now, I mean, will help you, but still there is quite a big area that is not covered. With the client-side smart load balancing, everything is on the client side, and the client side is fully aware what is happening. We have a system which is 5.9 available. How it is done? One of our product is that we have 3 independent instances of our product working in 2 different cloud providers in 3 regions. So even if AWS is completely down, we can still work. We have an instance in Azure. But having the client that is aware there are 3 service instances that I could contact with, and if one of them failed and another one will be available, it's the client responsibility to pull through them one by one to find a service which is currently available. So in one service, I could have just 2.5 nines, but if I have 3 independent instances, I can come up to the 5 nines. So client-side smart load balancing, it's a very cool one. How we do it? What we applied? We are using the service mesh. I don't know how far you are familiar with the service mesh. I'm not going to explain it, but basically there is a Istio, the most popular one, and we are actually using the Linkerd because the Linkerd turned out to be faster, more reliable, and more resource it consumes. So instead of applying all this Resilience4j patterns like retry, time breaker, time limiter, and a circuit breaker, we simply delegate that to the Linkerd, to the sidecar, to the smart load balancer. This is very, very good one because actually it has the internal logic to not create and to avoid this retry storm or any other orphan processes that you need to take care of yourself. So it is really cool library. So there are 3 takeaways that I would want you to stay with you. So first, resiliency need to be applied on the multiple level. It's not just one library will heal your software. No, definitely not. There is a very complex patterns that you can apply on different level of your application. Resilience4j library covers only part of available software patterns. And if you need to use those patterns, you need to prepare your application to using it, right? So it's not that you just take it and use it. Your application needs to be idempotent. You need to make sure that you can cover the retries, and that's element. And there are some references. So that would be it. I don't know how we are. Actually, we are just about to close. I'm working for Motorola Solution. We have a stand over there in the corner. I will be there for the end of the day. So if you have any question, if you would want to talk with me about any of the resiliency or any of the highly available solutions that we have, I'm really glad to talk with you, to answer your questions. And of course, I encourage you to come and see what kind of project we have, what kind of product we use, what kind of technology we'll use, so understand I can explain that concept even more. Thank you very much.